All right. Let's talk about binary arithmetic, and we have signed numbers, binary addition, binary subtraction, and then we get into systems that make binary arithmetic a little bit easier than having to use the carry and so on. And then we talk about the concept of overflow, and we also talk a little bit about floating numbers, floating point numbers. All the numbers we talked about, for example, we had 19, we had 25, 0, 0, 1, 1, 0, 0, 1. That's a 7-bit number. That's 25, right? It's 1, 2, 4, 8, 16. So that's 25. And what if we want to represent the minus 25? Well, one way of doing that would be to put a 0 for plus and a 1 for minus. So if this is 25, this is plus 25, and then this becomes minus 25. This is called sign and magnitude representation, meaning that there is a magnitude part, there is a sign part, and you put them together, and that's the representation there. This leftmost bit is called the sign bit. Okay, the sign and magnitude representation is good, it's simple, and you can easily look at the left hand side, drop it, and then you know the equivalent magnitude part. But then for arithmetic, that's not a very easy to do. So let's talk about arithmetic, and then we come back to other representations that make the arithmetic or subtraction a little bit easier. Well, why do I say for arithmetic that's not easy to do? Let's say you want to do 25, or let's say you want to do 93 minus 25. So what you have to do is to take you have to subtract 93 from 25, and then you will be using a mechanism for subtraction. Okay, let's go through the mechanism for addition for now. Okay, here I have two numbers. What are these numbers? This is 1, the weights, 1, 2, 4, 8, 16, 32, 64, 128. Okay, so A is 64 plus 8, that's 72, 74, so A is 75, and B is 32 plus 8, that's 40, 44, that's 45. Okay, and I am adding these two, and hopefully I'm coming up with 0 and 112. Okay, so the decimal becomes this. Now let's do the binary. Binary, I do exactly what we do in decimal, except that our digits are only 0 and 1, and the carry that we have is only either 0 or 1. See, if you add two decimal digits, the carry can be from 0 to 9, and so you add, let's say 9 and 9. Well, I'm sorry, you add 2 digits, and then you have a carry into the next position, and so on. So let's do the binary. 1, 1 is 0. You have a carry of 1. 1, 1, 1 is a 0. You have a carry of 1. 1, 0, 1 is a 0, carry of 1. 1, 1, 1 is a 1, carry of 1. 1, 0, 0 is a 1, carry of 0, no carry. and you have 001 is a 1 carry of 0, 010 is a 1 and no carry of 0, and 000 is 0. Okay, if I were to add these in decimal, I would do exactly the same thing. 5 and 5 is 0. You have a carry of 1, 1, 7, 4. You add the 3 together, that's 12, and then this becomes 112. So whether you do it in binary or you do it in decimal, you still have to have a carry, and the carry in the next position is either a 0 or a 1, just like what we have over here for 2-digit adding. Here this is 8, this is 16, this is 32, this is 64, 64 and 16, that's 80. 32 and 8 is 40, and therefore the result is 120 as we expected. All right, so this is binary addition, and the binary addition is just following the same basic rules. It's even easier than decimal addition, because here we are only dealing with 0 and 1. We have to repeat the same process more times, but in decimal we have to remember 8 plus 4 becomes 12. Okay, but then in well, that's easy for us now, but in binary we only need to remember 0 and 1. That's a 1 with a carry of 0, and 1 and 1 is a 0 with a carry of 1. And if you all have, you already have a carry from the previous position, 1, 1, 1 is a 1 with a carry of 1. All right, so this is binary addition, and now let's talk about binary subtraction. Okay, subtraction, it turns out, is not as pleasant or as easy as addition, but the same way with decimal subtraction. If you go back many years when you learned subtraction was always a little harder than addition because of the borrowing. Let's do a decimal subtraction. 237 minus 190, let's say 8. Okay, I want to subtract 8 from 7. I cannot, and therefore I make this 17, and then subtract this, and then I have a borrow from the previous position, and therefore this becomes 2, 9. I cannot subtract this. Okay, so this becomes 2. 9 from 2, I cannot do this, and therefore I do another borrowing, and this becomes 3, and then this becomes 0. Okay, and so I had to borrow, and for binary I basically do the same thing. Let's perform some subtraction. I'm gonna go back and get these two numbers. This is 75 minus 45. Okay, 0, 1, 0, 0, 1, 0, 1, 1. 0, 1, 0, 0, 1, 0, 1, 1. That's 75 minus 45. Okay. 0, 0, 1, 0. 1101. Okay, let's perform this subtraction. 1 from 1 is 0. Okay, 0 plus 1, 0 from 1. Okay, I cannot do that. The 1 from 1 is 0. Okay, yeah, 0 from 1, that I can do. 1 from 0, I cannot do that. Okay, Because I cannot do this, I borrow from the previous position. I add a 1 to this, and then that 1 added to this or borrowed from here becomes a 2 here, and therefore 1 from 2 becomes a 1. And then I have a 2 here. 2 from 1 I cannot subtract, so I add a 1 here, I add a 2 here, so this becomes the top 1 becomes all 3. Subtracting 2 from 3, that's a 1. This is a 1 in this position here, and I want to subtract it from 0. I cannot, so I add a 1 here, that becomes a 2. Now I can subtract a 1 from a 2, that's a 1. All right. Next position, I have a 1 here, okay, that I cannot subtract from 0, so I make this a 2, add a 1 to this, or actually borrowing from the previous position. 2 from 2, that's a 0. 1 from 1, that's a 0. 0 from 0, that's a 0. Okay, and what did I come up with? Let's look. This is 1. Weight 1, weight, let's use a different color here. Okay, weight 1, 2, 4, 8, 16, and 16 and 4 is 20, 8 and 2 is 10, so 20, 10, so altogether that's 30, and therefore you see that my subtraction is good. I used borrow. Well, the problem is if you go back, you find that, let's go back here, when I did the addition, I used a different process for adding than subtracting. Okay, here it was much easier. Here I had to do the borrowing. If I am to use do the subtraction and addition in different mechanisms, with different mechanism, what it means is when I get to the point where I need to build a hardware for it, the hardware for these two will be different. And so there will be one piece of hardware built for performing adding, another piece of hardware built for performing subtracting. And so that's one problem. The other problem is if I still haven't shown any way of representing negative numbers except the sign and magnitude. What I like to do is to be able to go through the same procedure for add and subtraction, and that procedure will, if I turn it into a hardware, will be the same hardware. So this is how I'm going to do it. I'm going to say that instead of using sign and magnitude, for example, instead of using a 1 in the leftmost position for 25 to make it minus 25, I'm going to use a different procedure. I use what is called 2's complement numbers. 2's complement does this. Complements all the bits, okay, 0, 0, 0, 1, 1, 0, 0, 1, that's 25. Complement all the bits, and that is 1 becomes a 0, 0 becomes a 1, 0 becomes a 1, 1, 1, 0, 0, 0. All right, so that's complementing all the bits, and then add a 1 to it. Adding a 1 becomes 1, 1, 1, 0, 0, 1, 1, 1, and the result is minus 25. Okay, and the result is what I regard as minus 25 in 2's complement system. What's good about 2's complement system? 2's complement, the good thing is that I can do adding, I can do subtracting by using the same procedure as I did for adding. Now, what's bad about 2's complement system? Well, 2's complement system, if I give you this number and tell you what the equivalent to this is, it's not like the sign and magnitude that you only look at the sign bit and then take the magnitude. What you have to do is turning it back into its positive equivalent, and then tell me what the this number is. So to turn it into its positive equivalent is again complement all the bits 0, 0, 0, 1, 1, 0, 0, 0, add a 1 to it, that becomes 1, 1, 0, 0, 1. Okay, now let's this is weight 1, 2, 4, 8, 16. Okay, so this is 25. Now that you have 25, that's plus 25, then you say, well, if this was 25, because I went through this procedure and found 25, therefore this is minus 25. Okay, so this is minus 25. And so the procedure is a little bit more difficult than the sign add magnitude, but the beauty of it is that you can very easily add and subtract, as we will be seeing next. Here I'm adding number 93 to minus 25. Okay, where do I get minus 25? Not by only complementing the, not by only putting a 1, but by the procedure that I showed over here. So minus 25 in 2's complement system is this. 1, 1, 1, 0, 0, 1, 1, 1. Now let's add these two numbers together using the add procedure. Okay, 1 and 1 is 0, a 1, 1, 0, 1 is a 0, a 1, 1, 1, 1 is a 1, a 1, 1, 1, 0 is a 0. Okay, carry of 1, 1, 1 is a 0. I'm sorry, 1, 1, 0 is a 0. Carry of 1. 1, 1, 0 is a 0. Carry of 1. 1, 0, 1 is a 0. Carry of 1. 1, 1, 1 is a 1. Carry of 1. 1, 0, 1 is a 0. Carry of 1. Okay. I added two 8-bit numbers and I ended up with a 1 on the left hand side. Okay, in 2's complement addition, if you are adding two 8-bit numbers and you end up with a 1 in the 9th position, you simply ignore that. Okay, you ignore that, and therefore what you have here is 0, 1, 0, 0, 0, 1, 0, 0. The weight is 1, 2, 4, 8, 16, 32, 64, and then the result is 68. And if you subtract the 25 from 93 is 5 from 13 is 8. A borrow, this becomes 3, becomes 68. Okay, and you just drop the 9th bit. That's if you're doing 8-bit 2's complement addition. If you're doing 16-bit, then the 17th bit will be dropped. So what you're really doing is, instead of subtracting b from a, or instead of performing a minus b, you are performing addition, but then subtracting but then using the negative b, and the negative b is in 2's complement system, and that's why it makes it very easy to do the adding, except the problem would be to come up with this 2's complement equivalent of it. And well, 2's complement equivalent of numbers is not that difficult. One way is to complement all the bits, add a 1. Another way is to, let's say, for example, 93. This is 0, 1, 0, 1, 1, 1, 0, 1. That's plus 93. Okay, now minus 93. Start from the right hand side. This is a 1. And then include the first 1, and then beyond that, or on the left of that, complement everything else. So that's a 1, 0, 0, 0, 1, 0, 1. Okay, so this is minus 93. And minus 25, start from the right hand side, keep the first one, and then complement everything else. So this becomes a 0, 0, 1, 1, 0, 0, 0. Okay, so that's plus 25. So going from plus to minus, minus to plus is the same way. Let's do one more exercise here. Let's see what this becomes. Let's see what this becomes in 2's complement, the negative equivalent of it, or the negative of this number, whatever this number is. So start from the right hand side, write everything as is until you get to the first one. After that, complement everything else. Okay? What is this? This is 0, 1, 2, 4, 8, 16, 32. Okay? I'm sorry. The weights are 1, 2, 4, 8, 16, 32, 64. That's 96, 100, that's 108. Okay, and therefore this is minus 108 in 2's complement system. Okay, fine. We have covered binary numbers, fractional parts, hexadecimal parts, adding, subtracting, and also we cover sign and magnitude, which is something that we are not going to be using very often, because the problem with the sign and magnitude numbers is that they're not very good for performing arithmetic. If you only want to represent numbers, that's an easy way of doing it. But if you want to perform addition, subtraction, or something, some arithmetic, that's not going to be a good thing. And then you use 2's complement system. When I say that we are representing something in 2's complement system, we are giving it a size as well. Remember that we say that the leftmost bit is always the sign bit. Okay, what it means is that I have to know the size, and therefore when you are dealing with numbers, you also have to know how many bits you are allocating for those numbers. So let's say in all the work we have done so far, we are using 8 bits for representing our numbers, and therefore when we say the bit to the left, we drop that. It means that the 9th bit is gone. So 8-bit is what we are dealing with for now. Now let's add 2 numbers, okay? And I'm going to go through the regular procedure for adding. 0 and 0, that's a 0. Let me use a more darker color. 0 and 0 is a 0, and the carry is 0. 0, 1, 1 is a 0, carry is 1. 1, 0, 0 is a 1, carry is 0, a 1. And then a 0 here, a 1, a 1, a 0, a carry of 1. Okay. 1, 1 is a 0, carry of 1. And then I add 1, 0, 0. That's a 1, carry of 0. Okay. 0, 1, 1. That's a 0, carry of 1. Okay. And then, as we said, this is 1, 2, 3, 4, 5, 6, 7, 8. This is where my limit is. And as before, I dropped the leftmost bit. But then something bad happened here. Look at the first number. Whatever it is a negative number. Why? Because the sign bit is 1. Whatever the second number is also a negative number. Why? Because the sign bit is 1. I'm adding 2 negative numbers. I'm coming up with a positive number. Forget about this bit here, okay? Because we drop that bit all the time. Anything beyond 8-bit, if you're doing 8-bit arithmetic, or anything beyond 16 bits, if you're doing 16-bit arithmetic, you drop that. And then you're adding 2 negative numbers. You're coming up with a positive number, but that's bad. What it means is that the result requires more space than 8 bits. This situation is called an overflow. Let me do another overflow for you. Let's say 1, 0, something like this. Okay. Let's add these two positive numbers. See, this is the sign bit, and therefore the two numbers I'm showing are both positive. 1, 1, 0, a carry of 1. 1, 0, 0 is a 1, carry of 0. 0, 0, 0 is a 0, carry of 0. 0, 1, 1 is a 0, carry of 1. 1, 1, 0 is a 0, carry of 1. 1, 0, 1 is a 0, carry of 1. 1, 1, 1 is a 1, carry of 1. 0, 0 is a 1. Well, unfortunately, again, what I have here in this situation, I have two zeros for the sign bits of the two numbers I'm adding, but then my result is a negative number. Okay, these two cases I call overflow. This one is overflow resulting in positive number for two negative numbers. This is an overflow for which results in a negative number for two positive numbers. What does overflow mean? Overflow, like I said, means that you need more space than you are giving it, and therefore you can either call it overflow and say, well, sorry, there is nothing else I can do, or decide that, well, 8 bits is not enough, go up to the next increment, go up to 16 bits. And then if you are going to 16 bits, you do what is called sign extension. So let's do this, for example. If I were to extend this into 16 bits, I would put 1, 2, 3, 4, 5, 6, 7, 8 zeros here. I would put 8 zeros to the left of this. Okay? When I do this, when I add these two numbers, when I get to this position, this is a 1, then 0, 0, 0, 0, 0, 0, 0, 0. So adding these two numbers in 16 bits results, two positive numbers results in a positive number. So I have remedied the overflow. For negative numbers, you basically do the same thing. You extend the sign. So this slide I'm showing extending the sign. So 1, 2, 3, 4, 5, 6, 7, 8. This is the original sign bit. Okay? And then you extend this all the way to make it a 16-bit number. Now I have two negative 16-bit numbers. Let's perform the addition. 0, 0. 1, 1 is 0, 1. 1, 0 in 2's complement system, right? In 2's complement 16-bit arithmetic. 1, 0, 0 is a 1, a 0, a 1, a 0 is a 1, a 0, a 0, a 1, a 0, a 1, a 1, 0, 0 is a 1, a carry of 0, with 1 is a 0, it is a 1. From this point on, a 1, a 1, a 1, a 1, a 1, all the way to here, a 1 in here, and then you have the 17th position, which is a 1, which we have learned to ignore, okay, or to drop. And therefore, now you are looking at these two numbers, you are saying, well, there is a 16-bit negative number on top, there is a 16-bit negative number at the bottom, this is A, this is B, and then the result is a 16-bit negative number, so you don't have an overflow anymore, you are good. So how do you correct overflow? By extending the number. How do you extend the number? For positive numbers, you put zeros on the left. For negative numbers, you put ones on the left. Or you perform sign extension.